with the experimental results. So, and then we have the another, it was the application of the mass and energy balance. So first, like when you see that the problem, you need to know about your system first. For example, we have, you want to calculate for the mass and then the energy balance. So we need to know like what's the system. This is open, closed, adiabatic, or even like your system, it was the steady state, open steady state. So we need to sketch. That's why like every time you need to, when you did the thermodynamics, when you try to solve about the thermodynamics, please do the sketch. So without the sketch, like you cannot imagine like your system. Is it your system is correct or not? So because like you need to know about the systems, is it which kind of the system you choose, and then how about the mass and balance? Is it the mass and balance, it's and mass and energy balance is correct or not, because we need to double check with the calculation in and out. And then after that, we need to know about the HU and the enthalpy and the internal energy. So this is mostly happen in the calculations, and then you can use the PVT like the pressure, volume, the temperature, or even we can use the sum function like function PT. So or the thermal function like U function of the TV. And then we will count the balance equation, like how much the parameter that you know. This is the function, the pressure, temperature, mass, soft work, and heat flow. And then if the number of unknown it's equal to the number of equations, so the problem can be solved. But if you have supposed to be the number of unknown is larger than your number of equations, so you need some additional balance equation. So this is one example that in the chapter 4, in the entropy balance equation, like you would like to discuss about the some problem you need to be solved, but we cannot just depend on the mass and energy balance. It's not enough. Somehow we need the additional balance equation, for example, entropy balance equation. I guess like we have later the some illustration that even we cannot solve because we need to know about the energy balance, entropy balance, so then we can solve the problems. Okay, so the illustration 341, this is basically like to discuss about the steam at 400 bar and 500 degrees C undergoes a Joule-Thomson expansion. Remember Joule-Thomson expansion, floating valve, this is all is isenthalpic conditions. So we want to release the pressure is from 400 bar into 21 bar. So please determine the temperature of the steam after the expansion using the figure 331A or figure the 331B, and also the steam tables in appendix A3. So basically like all of this figure will give you the similar answer, only that the accuracy like a little bit difference because it's visual for the figures, and a little bit difference value a little. But the most convenient, of course, is the steam table, yeah? So we can use the, okay, so because here like the molar diagram, so we can start, for example, like in here I can use basically like the way how you read the curve is similar like we discussed before, but here we can use the steam table, it's much more easy. So because in this case like Joule-Thomson equation, so the H1, it's equal to the H1 in here the T1, P1. So this one, it's equal to the H cap for the T2, P2. So it's equal to the H2 cap. Then, if you would like to calculate for the steam table, of course, you need to know about the, in appendix, we have the, at the 40 megapascal. So for the P1, you have the 400 bar. So we want to know, like we can convert to megapascal. And then for the T1, it's equal to the 400 degrees C. So this one, you have the H1, it's equal to the 2000 H cap 2903, yeah, 2903.3 kilojoule per kilogram. Okay, this is for the H1. And then for the P2, because we want to release, there should be 1 bar. and 0.1 megapascal. Right. So then we have the H because the temperature is Joule-Thomson equation. So the T it's equal to for discuss you don't have the T2, right? But you just give they just give for the P2. So it means that isenthalpic condition you can use the same H, and then you can read in the from the steam table that how much the T2. So we can use in here like P2, and then for the pressures, and we can if the H is similar. So we can see like in the steam table for the H that they are occupied or in the between of this H because the enthalpy the same. So we need to know that the interpolation, because you don't know T2, so you need to read. This is at the T is equal to 100 degrees C. This is from steam table. Yeah. This is from steam table. You can get this data. And then the other for the H cap, you have the data from the steam table 2974.3 kilojoule per kilogram. This is you have at 250 degrees C. Then because you have the H1 is equal to 2903.3, and then how much the T2 exactly, like it should be in the between of this. So if you have the T, because we don't know the T2, then we need to know, like we can use the interpolation. Isenthalpic condition, enthalpy the same, but the T2 is not, the temperature is different. So we can use the interpolation. I believe all of you know how to do the interpolation. I just go directly to the calculation. So we have the multiple 29 because it's 2903.3 minus 2875.3 divided by 2974.3 minus 2875.3. Then here it's equal to 214.1 degrees C. Even you calculate with the Euler diagram figure based on the 331 or 332, the result will be the same. It's around 214.1 degrees C. Even use Aspen. If you use Aspen to simulate this, I think the result is around 215. So it's not that far. Of course, like they will have difference because the accuracy, like even you read the curve, like every people, they have different scale. So they have the uncertainty for this case. So of course, like the most accurate one, it's by the steam table because we just use the interpolations, yeah, and then you can calculate this. And we can go to the illustration 340. I think in the illustration 342 is a simple case. We do almost similar like before, so I don't think that it's hard for you. And then we can go for the illustration 343. So in the 340, it's exactly like the compressed air tank is to be repressurized to 40 bar by being connected to the high pressure line. So here we have the pressure line, 50 bar, and then 20 degrees C. You connect to the cylinder, and the repressurization of the tank occurs so quickly that the process can be assumed to be adiabatic. So there is no heat transfer from the air into the tank. And assume that CV asterisk is equal to 21 joule per mole K. So then we don't have Q, so Q is equal to be 0. So then if the tank is initially contains air at 1 bar, so in the tank initially, if supposed to be have the 1 bar and 20 degrees C, what will be the temperature of the air in the tank at the end of the filling process? So T2 is how much? And then if you have the big case, after the filling such long period of the tank, and the room temperature is 20 degrees C. So because we have the heat exchange between the cylinder and then the atmosphere, so what is the pressure of the air in the tank? So in this case, after the sketch, you need to assume. So what we can assume? Of course, in the Q equal to be 0, in the problem say that no heat loss. Then what else? No energy kinetic and energy potential like before. So when we go to the energy balance, you can assume that this is neglect, and then you can consider that this is to be ideal gas. It's just to simplify the problem. So it means that your Cp, it will be equal to the constant. Okay, so we can start that this system, it's not closed, but it's open because like you transfer the gas from the outside go to the inside. So the system itself, we can write here the contents of the tank. Yeah, you can say tank or cylinder, it's okay, no wonder. So this is open system. Okay, so then we start with the mole balance. Okay, I can start here with the mole balance. Mole balance. Remember open system, mass flow in and out and energy in and out. So we have the N2 minus N1. So here will be equal to delta N. And then we have also energy balance. When I write directly, can you understand? So you can try to expand from the general. I just write in here like the hint, yeah, because from the previous, like we expand the equation directly. So you have du divided dt plus energy kinetic plus energy potential equal to the sigma of the enthalpy energy kinetic energy potential plus Q plus W. So in this case, because you have cylinder tank, do you have work in tank? We don't have work in the tank. And then we can for the force dv divided dt, and then a steady state process or not. So you can assume it's depend on your system. But here is open system. I can simplify my equation because we don't have the kinetic and potential. So it means we have N2 U2 minus N1 U1, yeah, equal to Q. Q is so equal to be 0. So it's only have delta N multiplied by H in, right? Why is in here like H in? I simplify by H in because the tank in the problem say that it's repressurization. So it means that repressurization. Sorry. So here, yeah, repressurization. So repressurization, it means that the system, it was too fast, and then is the flow, it's really flowing so fast. So you can assume that it should be like it's isenthalpic condition. So H in is equal to the H in. So the source air, they will not change. Source air, they are at constant T and P. So in this case, like we can say that the H in, the enthalpy in is to be constant. So H in is constant. H in is constant, equal to constant. Okay, so then this is, I need to write the underline because it's small. Then after that, we can go for the next. It was how to solve the problem, because they asked like if you have the problem, if the tank initially consists of the 1 bar and 20 degrees C, what will be the temperature in the air in the end? So we can start with the calculation is for ideal gas. That's why we need to assume the ideal gas. Actually, to simplify the mathematic problem, if you need to the real gas, this is not in this chapter. Later, like we have for the real gas. So this is function of the temperature assumption, yeah, because it's constant. So then we have the enthalpy, because here it's kept. So Cp asterisk, remember, T minus Tr. This is we discussed before. And then you underline for the T, it's mean Cv asterisk T minus Tr. So then minus R Tr. This one is the first equation. So or in your textbook, they have the in equation 248, I think. And then in here, like this is the reference states. So the reference states we can assume to be 0 because it's ideal gas. So Tr, it's equal to be 0, or you can say H, this is equal to be 0 for the reference. For the reference state, yeah. And then we can use the energy balance equations. becomes, so N2 here, CV asterisk T2 minus TR, because here like T2 minus TR, you can substitute this one. It means U2, yeah. Minus RTR, this one, minus N1, CV asterisk T1 minus TR minus RTR. Okay, so this one, from where this equation coming from? From here, yeah, because in energy balance U2 we can replace with these equations. And then after that, we can write in here N2, simplify, minus N1, and then CV asterisk T2 minus TR minus RTR. This is, we can replace with the CP asterisk, and then T in minus TR. So same, yeah, like the previous, like because we have in here delta N H in. So this one, or I think it's more easy if I write in the beside. So let me find the, okay, I think it's to make you more easily to understand. I just write here, because here it's in the one equation, so we can write N2 minus N1. So here is CP asterisk T in, T temperature inlet minus TR. Then here we can simplify the equations, become the second equation, CV asterisk T2 minus N1, because TR, everything TR, it's going to be 0, so you don't need to consider about the reference temperature. So here you have only T in. Okay. Okay, temperature in, yeah. So here it's not really clear. So this is the second one. And then after that, if you have the constant, because like N1 and divided by N2, so we can replace this term into to the ideal gas. I will change the color into to the blue. So we will use this one, use the ideal gas equations to change. So for the ideal gas, we can use the P1 V1 divided P2 V2, right? And then here N1 R T1 divided N2 R T2. Or you can simplify N1 divided N2 equal to the P1 T2 divided P2 T1. So you can use this equation, basically substitute into to the second equation and introduce this, and then you will get the T2 equal to the P2 divided, substitute to here and rearrange the equations. So this is from P2, P1 divided T1 plus CV asterisk divided CP asterisk, and then you will get P2 minus P1 divided T in, temperature in. So this is normally from equation 3 into equation 2. Okay. Okay. Then if you have, because in this problem, it's given that since the P1, okay, here, like we have the since P1 it's equal to 1 bar, and then we can, the problem, they say that T1 it's also 20 degrees C, and then you have the P2 is originally 40 bar, yeah, 40 bar. And then we can see via asterisk, you have the 21 joule per mole K. and we can calculate the Cp asterisk is from the Cv asterisk plus R. So then we can calculate for the T2 basically. It's from the previous equation from here, yeah, from the originally yields for the equation 3 into to the equation 2. Then we can get the T2 is exactly like 405.2K. So this is around 132.05 degree C. Then the next question, if the P0, if the P1 is initially is evacuated or is in the vacuum condition, we can calculate for the T2 exactly by the Cp asterisk divided Cv asterisk multiplied by temperature in. This is not function of the pressure 2 like the before, because you have the, for example, is initially evacuated, so you only have Cp asterisk divided by Cv asterisk because your P1 is equal to 0, so it's not depend on the P2. In this is not function of the P2. We can simplify this, so we can calculate the Cp asterisk divided Cv asterisk. This should be larger than 1, or you can say that T2 is larger than temperature in. So this is what we have in the in the equations. Okay, the second, they're asking about for ideal gas for the constant V. Yeah, for ideal gases with constant V. Pf divided, you can simplify, use the F, it means final, or you can say 2, yeah, in this case P2 divided T2, the same. So we can use simple correlation. P2, you have Tf divided by T2. So here it means 40 multiplied by 293.15K divided 405.2K. So this, the pressure, it's equal to 28.94 bar. For mechanical energy balance, you can do this way, but for the temperature, we cannot use this way, because like this is two different concept. Like we cannot use this concept for the temperature, but we can use for the mechanical energy balance. Okay, so you can use the final states like the comparison simple for the mechanical pressures. But for the illustration 345, this is expansion from the 343. That's why when you go to the Sandler book, you need to understand like the each of the illustration, because once you miss one of this, it's difficult to understand, go to the next step. So that's why I suggest to all of you to understand like each of the illustration, it's much better. This is interesting. We have the gas cylinder of 1 meter cubic volume containing nitrogen. Initially, you have the pressure 40 bar and the temperature 200 K is connected to another cylinder. So it means like you have two cylinders, they are connect each other. And then the 1 meter cubic volume that is evacuated. So originally, like another cylinder, they are evacuated. So the valve between the two cylinder is open. So we want to transfer from the another cylinder, go to from the one cylinder, go to the second cylinder. Then we open until the pressure is equalized. Equalized, it means that the pressure is the same. And then find the temperature pressure in each cylinder. So we need to know the T and P at each cylinder. And then if there is no heat flow in and out, you don't have Q in this case between the gas cylinder, so you assume it to be 0. And you may assume that the ideal gas and the constant pressure with the heat capacity Cp is equal to 29.3. That's why I suggest to sketch. So here we can sketch. I think I just take some space here. So we can sketch first. Like I have the just small here. Yeah. So for example, like I have this cylinder. This is cylinder 1. Yeah. So I want to transfer the cylinder by the valve into to the second. So I have the second cylinder here. Okay. And then in here, I have 1 meter cubic. So the volume here, 1 meter cubic. The other also the same, 1 meter cubic for the nitrogen, N2, N2. So what I'm going to do next? So the next, like we need to assume, yeah, of course, assumptions. Assumptions that the Cp asterisk for the N2, it's given 29.3 joule per mole K. And N2 behave as ideal gas. N2 behave as ideal gas. So you can assume in ideal gas for this chapter, no worries, but for next chapter cannot, yeah. So here we have the P10 is equal to 40 bar. And then the other, it was for the T10, this is initial. When I write 0 here, it means initial, or it start with this number 200K. Then the same for P20, this is 0 bar. And then for T20, it's equal to, we don't know. This is what we're going to ask. We want to know. And then please find this following. We have the P1F. We don't know the final condition. T1 final. And then we need to know the P2F. We need to know the T2F, because the final condition we don't know. That's the one that find the final temperature and pressure in each cylinder. So it means that we don't know that the system. So system, it was the interconnected of the gas. Yeah, this is the gas cylinder, and this is closed system, because you don't transfer to outside. Yeah, system, close. Okay, system. They are interconnected each other. So how are we going to solve this problem? First, the same, mole balance. Mole balance, mole balance. So you need to know the mole balance here. You have the N1, I, the initial one, equal to the N1 final plus N2 final. Okay. So in this case, this is the first equation from the mole balance. And then the other is energy balance. So energy balance, you have the N1U1. So here, don't forget underline. This is, I give initial, equal to the N1U1 final. This is the same final plus N2 final, U2 final. So hopefully you already know, like when I write U, it means like you don't have the Q plus W, yeah, it's tank. So you don't have this. So you don't need to worry about the other equations. Then since that the N equal to the PV divided by RT, ideal gas law, because PV equal to the nRT, so we have the V1 equal to V2 equal to the V, it's equal to 1 meter cubic. Then we can expand the equation 1. It's become like P1 initial divided T1 initial equal to the P1 final divided T1 final. So this is plus P2 final plus T2 final. So this one, we can write equation 3. Why? Because the initial, we transfer the initial one, go to the second one until they get until the pressure is equalized. Then for the ideal gases with the CV asterisk and Cp asterisk. So here is not equal to the function of the temperature, yeah. This is in assumption. So we can write Ut equal to the CV asterisk T, yeah, minus CP asterisk TR. And this is from the assumptions. This one we can write in equation 4. Then from the equation 2, we can divide this equation because we have the P1 T1, and the P1 T1 here we can combine to the energy balance. So we can replace P1 divided by T1. So with the NN in the equation 2, we can replace with the P1I divided T1I and so on. And U in here also can substitute from the equation 4. Therefore, this equation, it's become P1I divided by T1I Okay, so here the full equations, or you can simplify like this. Become minus Okay, so in this case, like because this one it's equal, this is mass balance, yeah. So this one is mass balance. So you don't have this one. This all is mole balance. So this equal to be 0. Mole balance. So you only have P1 initial equal to the P1 final plus P2 final. So this one, it's equation 5. So we can use the mechanical energy, mechanical equilibrium, yeah, like before, mechanical equilibrium. So we have in here P1F equal to the P2F. So you have the P1F equal to the P2F. This is equal to the half of the initial because it's in the problem say that it's equalized. So it means you only have this one. So it's equal to 20 bar. And then for the temperature is spatial because we cannot make the temperature is equal to the mechanical energy balance. So it means that we need to solve the temperature. So from the equation 3, I believe that if you still remember equation 3, yeah. So this is equation 3. So we can use this equation 3 to calculate for the temperature. So from equation 3, so we get the 1 divided by T1 final because the pressure is the same. So we can just write like this, equal to 2 divided T1 initial. So this become 2 divided 200 and then 1 divided 100. Number 6 is temperature. So this is equation number 6. So from this you know, right? Because in here we have the two unknowns. This is we don't know, the T1F we don't know, T2 also we don't know. We doesn't know that this one how much the temperature T1 and T2. So it means that we need two independent equations to calculate because we need to know the temperature. Then because in this case like we don't have the enough equation, so we need to assume another system. So the another system in here, we can use the system, just take one cylinder, or here I take the cylinder 1, just one cylinder, but because the cylinder 1 it's who transfer the gas to the cylinder 2, so we can take the cylinder 1, this is as the open system because the gas is go out from the cylinder 1. So we can take as open system and we can solve the mole balance the same. You need to divide mole balance. It's from the N1 divided by dt equal to the N dot. This is its equation 7. And then the energy balance the same. dN1 U1 yeah, divided by dt equal to the n dot h1. This is equation number 8. Then we do the integrations of these equations. The energy balance integral. So we have N1 final, U1 final, minus N1 U1 initials in here. So it's equal to the integral N H1 dt. But you see that this one, the H1, they are not constant. So I think if we solve like this way, so it's more challenging because you need to depend on the temperature. And the temperature, they are changed. T1 and T2 is not the same. So what we can do? We can use simple way. The equation, from the equation 8, we can differentiate. Use the right in differential form for the equation 8. This is to help you to solve the problem. So dN1 U1. So in here, we can do like this, divided by dt. And then, okay, so if you write this form, it means that your H1 is constant. So this one, it's equal to dNi d1 dN1 divided by dt from the previous equation. So it's more easy compared than you divide by the temperature. So we can rewrite these equations. It's become like N1 du1 divided by dt. It's equal to the H1 minus U1 dN1 divided by dt. So this is equation 9. Then for an ideal gas, because we assume that for the ideal gas, so we can use N equal to the PV divided by RT. So here you have also for the H, we can use Cp asterisk T minus Tr, yeah, for the reference states. Then for the U also we can use the Cv asterisk in here T minus Tr minus R Tr. Then these two we can combine with this equation H1U1, because here the N1 is equal to the PV divided by RT. So we can simplify that the H1 minus U1 equal to the RT1. Yeah, H equal to the U plus PV. PV in ideal gas equal to the RT. So the equation 9 becomes P1V divided RT1 is equal to the N Cv asterisk dt1 divided by dt equal to the RT1 d differential divided by dt P1V divided by RT1. So you can neglect each other here. So V, you can remove the V. And then in here, what else? You have the R the same. So then we can rewrite or Cv asterisk divided by R dln T1 divided by dt. So here equal to the d divided by dt ln. Okay, and integral this equation. So you will have T1 F this is equal to 0.5. Why 0.5? Because before is 1, we have the case is half, yeah, half it's equalized. So it means that in here we have the T1F. We have 2 divided to before for the T, it's equal to 2 divided to 100. It's equal to the 1 divided 100. So then in here we have the T1F, it means that you substitute all of the value here we have. So it means 164 Kelvin. So you know everything's in this problem, in this, you know the value of this for the P1F and then P1I, you have T1F, and then you don't have T1F, you calculate, and T1I you know, and then you can just calculate, so you will get 164.3 K. Then we can solve another from equation 6. So like the previous, we have the equation 6 from this one. Yeah, so we have the 2 divided 200 equal 1 divided 100. So we have T1F, and then we can calculate for the T2F. So from this equation, we can calculate based on these equations. 1 divided T1F plus 1 divided T2F equal to the 1 divided 100. Then you have the T1F from the previous, so here you have 255.6 K. Okay, so it's not difficult, right? So since the N1 still not finished yet, we have V1 P1F divided by RT1F. So here you can get the N1F, it's equal to the N1F, it means the number of mole after the equalize. So you have 64 mole. The same for the N2F, you need to calculate for the V2, P2F divided by RT2F. So here you will get N2F equal to 0.941 mole. Okay, so this is like for the next for this writing, and then for the ideal gas. So for how we solve everything for the ideal gas. And how about the real fluids? If you have real fluids, you need to consider about the pressure function of the TV. So it means, for example, you have the system A. It means you have P1F equal to P2F. You have the same N1F equal to the N2F equal to the N1. Yeah, initial. This is the first. This is the second. And then also we have the other for the N1F. This one, you need to calculate from the volume cylinder 1 divided by volume 1 final. So this one, it's for the equation 3. And then for the equation 4, we can write the energy balance. Yeah, the same for the N2F, also the same. So for the volume here, it means the same for V2. Yeah, I just write once of the representative T1F, P1F. It means that everything is function of the temperature and the pressures. So means that you need to know the many unknowns. It's around like 8 unknowns. If you want to solve the real fluids, you need to know about the equation of states. So in this case, like we don't have equation of state, so we cannot solve by this way. So for the V2, the same, yeah, the same. So you can this is V1 final. So you need to know also about the function T2, and then the final, and then P2 final. This is for the real fluids. And then the next, it was the illustration 346. So the 346, it was discussed about the pistons. Like, is it possible to go from the given temperature, like from the system to given final equilibrium state by the number difference of pads? So we have the 3 pads in here, pad A, pad B, and pad C. So pad A, it was the isothermal or constant temperature compression to 1 bar. So you see that initial state from 0 to the 10, and then they will go to the isobaric heating to 300 degrees C. And the pad B, it was, they go for the isobaric heating to 300 degrees C, and then follow the isothermal compression to 10 bar. And the pad C, it was the PV asterisk is constant, or PV gamma constant, and then gamma it was Cp asterisk divided by Cv asterisk, followed by the isobaric cooling or heating. So here isobaric PV compressions and then isobaric cooling or heating until 300. So in this case, like you have the initial and final, they are the same, but the path they are different. So how are we going to solve this problem? So first you need to know, like this is typically like piston. So if you draw the pistons, it's like this. Yes. So this is supposed to be, you have 1 gram mole. So you have state 1, you have state 2. So the function of this case is just to see that the property, which one is property, which one is the state property, which one is the path property. So you have 25 degrees C to 1 bar, and the other is 300. You want to go to 300 degrees C, and then you have 10 bar. So what's going to do with this? So remember that the system, it was the gas in the piston. So this is, it means closed system. You want to know about the, you need to find, like in this case, you need to find the Q, you need to find W, you need to find delta U. So is it the, which one is state property, which one it's the path property? So we can see from this energy balance, yeah, energy balance, it's coming from delta U equal to the Q plus W. So in this case, you have U2 minus U1 equal to the Q plus W. Remember that W in the piston, I will change directly into the work force. So if you saw that in the piston we have the work force, we don't have Ws. So minus integral P dV. So this is what we have in the pistons. And then we can use like to calculate for the W itself, W in the piston, because it's equal to minus integral P dV. So for the ideal gas, for the ideal gas law, so you have PV equal to the RT. So in this case, you can calculate for delta U, it's equal to integral Cv asterisk delta T. Okay, so remember that 3 hin in this case. You have 3 hin. For the isothermal process, it means that the temperature is equal. Right, so everything, it's a function of delta T, it's equal to B0. In this case, which one is function of the T? It's delta U. So in this case, delta U, it's equal to B0. In the isobaric process, when the pressure is the same, so it means that you have delta P, it's equal to B0. And we have another is adiabatic process. So you have Q equal to B0. So in this case, you have PV with the gamma. This is constant. They will not change. So the gamma itself, it's coming Cp asterisk divided from Cv asterisk. So you can get the results. If you supposed to be used that 3 equation, you can make table. This is for the Q, this is for W, this is for delta U, because delta U is equal to the Q plus W. So you can make the table for this path A, B, and C. Okay. So this path, yeah, path, and then this is Q, I just write joule per mole. And then here W, joule per mole. And then here you have the delta U. Delta U, it's coming from the energy balance. So you have the delta U equal to the Q plus W. So pet A from the result 4000, I will write to indicate the result. Okay, so we can see or determine from this case, like you see that the Q and W, they are totally like, even though the initial state and final state, they are similar, but the path is different. So you can see that the Q and W, each of the path, they have different results. So means that this is path functions. And how about delta U? Delta U doesn't matter, you go to path A, path B, path C. They are the same purpose, but the result is the same. So here it's mean state functions. This is what we discussed in the chapter 1 about the path function and the state function. So that's the reason why in the path function, whenever you go to the final state, even like it's different path, but the result is totally different. That's why the work, which one, for example, like if you would like to evaluate the sum processes, but you would like to know which one is more efficient. Is it the work is less or you need the more work to do this? If you have the more work to do this, it means that you need more energy to do this. So we go to the less work, it's much better compared than high work. But for delta U, it doesn't matter. All of the path are different, but this is a state function. So it doesn't matter. They will not affect with the path. So I think thank you very much for the chapter 3. So this is in the end of our lecture, because the lecture, I think for the illustration 347, it's actually like discuss about the pistons. But for the pistons, this one is not it's not that described that much about the chapter 3, but this is mostly like physics. So I think like for this part, it's outside of the scope of the chapter 3. So I think that's it for the chapter 3. Thank you very much for today. Good afternoon, everyone.